Good morning. It's about 8:32. I think we'll go ahead and get started. Welcome to day 4 of PDC. I certainly appreciate everybody being here at 8:30 in the morning. It's pretty early. My name is Pat Steeman. I'm a program manager on the kernel team at Microsoft for the Windows division. And this morning, I want to talk with you about building energy-efficient applications. Now, the title of the deck here, it has battery life in it. And I think we're going to learn today that there's more to it than extending battery life. It's also about reducing power consumption in desktop, in server, and other environments. And I think we're going to learn a lot about how run-of-the-mill applications have surprisingly large impact on power consumption and battery life. So it being 8:30 in the morning, I thought no better way to start than a PowerPoint chart. So what we've got here, I talked to some friends in Microsoft Research, and they're taking a survey of processor technologies. And they're looking at different metrics, the process technology it was built with, the number of transistors, performance, but they also looked at power. And the power data alone is very interesting. What we've got here is a survey of Intel processors and their maximum power consumption over the last 20 years. And so on the left, right about a watt and some change, old school 386SX. Very, very low power processor, and also very low performance relative to today's processors. And then on the far right, 20 years later, we're looking at quad-core, Core 2 Extreme, very, very rich performant processors, but they have a much larger power consumption. That Core 2 Extreme processor comes in at over 100 watt of maximum power consumption. And so the point here is that when we talk about energy efficiency and power consumption and battery life, the core components of computing are increasing their power consumption over time. And it's not just limited to processors. How many of us have graphics adapters in our desktop machines that require sideband power from the power supply? The PCI Express slot is no longer capable of providing enough power for that GPU. And we see the same thing in network devices with 10 gigabit and gigabit LAN. And we see it across lots and lots of different parts of computing. So power consumption is becoming a bigger part of the problem. But you might look at this chart and go, great, processors, GPUs, network adapters, those devices, they consume more power. So what's Microsoft doing in the latest version of Windows to correctly manage those devices? And the answer is we're doing a lot to correctly manage those devices. But it's not just the devices and the hardware. It's not just the core OS. It's not just the kernel. Applications and user mode software have big impact on power consumption. So more data for the second slide. We've been spending lots of time working with our partners in the industry to optimize the pre-installations that come with OEM systems. We want them to have great battery life, be very responsive and performant. And so one of the tests that we do when we work with a partner is we evaluate the battery life for the OEM installation versus the clean installation. It provides sort of the best case where that platform could be. Now, it's not realistic. Of course, we want OEM systems to ship with rich variety and lots of great software, but we want that software to be as optimized as possible. And so when we look at the battery life, we're seeing big differences in many cases between the pre-install and the clean install. And the bars that move to the right of this slide, they're showing you the additional battery life you get on the clean installation. And the difference here is all software. It's not hardware, it's not new devices, it's not new kernel changes, it's all application software. Now, there may be a few policy tweaks and that kind of thing, but the wide majority is application software. So the takeaway from these first two slides is that power consumption in modern computing, much bigger problem than it was 5, 10, 20 years ago. And it's not just the hardware, it's not just the core OS. Those applications that we put on the system, they have big impact on power consumption and battery life. So the plan for today, we're going to talk just a little bit more about energy efficiency and what's going on in the industry. I promise not too many more introductory slides. We're going to talk about our focus in Windows 7 on idle power and how we want to take that focus to the ecosystem and how we want to drive down idle power on systems to help extend battery life and reduce power consumption. And then we're going to spend the majority of the deck talking about optimization techniques. What do we do in our software to improve battery life, to reduce power consumption, to improve energy efficiency? And then we'll spend the last 5 or 10 minutes maybe 15, on diagnostic tools that we've built into Windows 7 and diagnostic tools that are available online today to help us find out how our applications are behaving, to help us find out what resources they're using, how much CPU time, how much disk, and what have you. Now, I pulled a fast one on the slide guys upstairs last night and added a new demo to the end of the deck. So hopefully we're going to have plenty of time to get through all of that today. The power consumption is going up for the devices that we run on. The software has a big part, and there's a lot of industry activity ongoing right now to deal with that. The first is this concept of all-day battery life. It's a great buzzword right now. Everybody wants all-day battery life. Sometimes they mean 6, sometimes they mean 8 hours. Well, in many cases, all-day battery life's here. This small machine with a large battery, it delivers 6, 7 hours of usable battery life. I often go several days without charging it from meeting to meeting. So look at all-day battery life and realize what we're really talking about is extending the mobile experience as long as possible. How long can you use your mobile device, whether it be a notebook of some varying size, before you have to charge it up? And as soon as the wide majority of systems meet the all-day category, we'll move on to something else. It'll be multi-day, or it'll be weekly, or whatever it's going to be. In fact, on this battery life point, we see a lot of this in the industry today. I've seen some of the OEMs have been competing recently on how long of battery life can you get. I heard fairly large numbers, 18, 19, 24, 26 hours on a single charge. Now, of course, those are small machines with big batteries often to help deliver that. But there is big interest in delivering this as long as possible mobile computing experience. When we talk about desktops and servers, it becomes less about mobility and more about how much does it cost to power that system. We're seeing really big concern in enterprise for desktop managed systems about how do we turn those displays off? How do we get those machines to go to sleep? How do we allow them to be powered down so that they're not running 24/7 and still do things like maintenance and patch management? And that's really driven by the cost of consuming the energy. And in some cases for servers, it's about the cost to cool those systems and manage them. But a really big interest, surprising interest, I would say, over the last 5 years. And how do we get our, have 100,000 desktop PCs in a given deployment? How do we get those to consume as little power as possible and still deliver great functionality? Regulatory compliance is also becoming a very big topic in the industry. Many of you are probably familiar with Energy Star, which is a requirement that PC manufacturers are meeting on some systems today. Well, the Energy Star requirement is not only about do you have the display set to go to sleep and do you have the system set to go to sleep after a timeout, but it's also about how much power does that system consume when it's idle. And we're going to learn today that the amount of power consumed when the system is idle is heavily influenced by application software. It's not just the operating system. It's not just the hardware components picked out for that system. It's also the apps that are running and loaded. We're seeing industry efficiency across hardware development. So many of the processor vendors are talking about performance per watt as the buzzword or the buzz phrase for energy efficiency. But hardware is starting to lead from the mobile, where energy efficiency was the primary driver for long battery life. We're seeing that driven into desktops. We're seeing that driven into servers as well, for all the other reasons above. There are 3 or 4 major environmental consortiums right now about how do we reduce the energy cost of computing to reduce the environmental cost of generating that energy. Climate Savers is one, Green Grid is another. There's a variety of interest out there in working through that. And then the last one here is product differentiation. And this is what I was talking about with the OEM battery life race. That's just one example. We're seeing green desktop PCs. We're seeing green hard drives marketed. We're seeing a variety of these technologies being marketed. And the reality is that it's not just limited to the hardware. The software can have big impact too. And that software, it can be differentiated on how much it helps battery life or how much, frankly, it hinders battery life or power consumption. When we were in the slide reviews back at Microsoft, they said, Pat, you've got to give them a plan. What is it that you're going to do to help everyone optimize their applications? And the answer is that the first thing we're going to do is understand that the applications, they have big impact on software and on power consumption. And then we're going to go after resource utilization. We're going to go after CPU time, disk time, memory amount, registry accesses, sleep and resume. We're going to break it down and go through each part of resource utilization on the system and learn how to optimize them as much as possible. We'll have a razor focus on idle. This is something that we've done for Windows 7 internally, is how do we reduce the power of idle, and we're going to see why on the next slide here, and how do we get our system to be, we call it get idle and stay idle inside Microsoft, but how do we get the system to be as idle for as long as possible to help you extend battery life and reduce power consumption. We're going to learn how our applications can adapt to system environment. One of the things we do is that we want to take, we might have an application that delivers great functionality and great value, but we might want to tone it down or quiesce it or reduce some of its functionality dynamically when the system's on battery power or when the system's in a power-saving mode by the user. We're going to talk a little bit about what's the right tool for the job. How do you know which kind of application you should build, what kinds of functionality you should have in your application based on power management and energy consumption and what have you. We're going to talk about sleep and resume transitions. In years past, sleep and resume was a much bigger problem than it is today. And very good news, we're starting to see applications do a fairly good job of handling sleep and resume correctly and seamlessly reconnecting to network resources. And we'll talk about this. It's a lot like handling intermittent network connectivity. And then validate and measure. So the last thing we're going to do is we'll look at the inbox tools we have for Windows 7. We'll talk about something called the Windows Performance Toolkit, which is in the hands-on labs here at PDC. We'll talk about how we measure those resource utilization issues from step 2. And then we'll work on it again and again and improve it as much as we can. So a big theme through today's talk is focusing on reducing idle power. Now, when we talk about client computing, we often talk about what's the scenario. People will say, I get 6 hours of battery life on my machine. And my immediate question is, doing what? 6 hours playing a game? 6 hours watching a DVD? 6 hours doing nothing? And in fact, even the industry benchmarks for measuring battery life, they all vary in terms of what is their scenario, what is their workload, what do they measure. But the good thing about idle is that idle is the foundation for all of those scenarios. Whether or not you're playing a DVD or you're letting the system sit there or you're working in an office or a productivity application, idle is always there. And the thing that we want to do as much as possible is reduce the idle floor, reduce the base power consumption of the system by either powering down devices or reducing the background activity of that software that's always running on the system. And again, the regulatory compliance issue comes back into idle. With Energy Star, systems are being measured for their idle power. And that idle power is influenced by the applications. So pretty chart and animation. We want to reduce the power here as much as possible. Now, applications, they don't simply sit there and be idle. Otherwise, there'd be no point to have them. So we also need to look at how do we reduce the workload? How do we reduce the power of performing that application functionality, performing the valuable work that our applications do? And there are a couple techniques that we're going to talk about. The obvious one is that sometimes we either want to trade quality or performance for power savings. So we might want to do something less often, or we might want to limit the amount of things we do. So a good example is search and indexing in Windows. Search and indexing only indexes high priority items when the system's on battery power, because we know that reduces the power consumption of that search and indexing workload. Another trick might be that we disable animations. So a good example of that is Arrow Glass in Windows Vista, right? If you go on Power Saver and you go on battery, it actually disables transparency in the windows to give you just a little bit more power savings and reducing the workload of rendering those transparencies. And then the last one here is that we might make playback optimizations in DVD is another example. So a common thing that we're seeing in retail DVD software is that content will be played back at 30 frames per second instead of the specified 60 frames per second. The user doesn't necessarily have a perceptible way of seeing the quality difference, but it consumes a lot less power. It reduces the amount of CPU time, it reduces the amount of GPU time, and delivers a great experience still for the user. The other way that we reduce, just flat off the top, workload power is performance optimizations. Anytime that we make a performance optimization, we use less CPU, we use less disk, less registry activity. It's always a win for power savings, always a win. So we look for ways to get rid of activity we didn't need to do. So if we're polling for some state in the system, we might try to eliminate that polling. Or if we can, extend the polling interval. We're going to dive more into that when we talk about timer coalescing here in a few slides. And then another good example of this is just eliminate periodic disk activity. We found a lot of applications and even a lot of components in Windows tend to have periodic disk activity, and it's not always required. Maybe it can be eliminated altogether, maybe it can be extended, maybe it can be disabled on battery power. And all of these things help reduce the power consumption of the workload in question. And then a more interesting and tricky one to explain is trying to coalesce the work and get it done quickly, even though it might consume higher power than it would otherwise. Sometimes we call this race to sleep. But the idea is that we want to be in the idle state as often as we can for as long as we can. So sometimes, depending on the workload and activity, it's better to get it done as quickly as possible, even going to a higher power state to get that done, and then to go sleep for a longer amount of time. A good example of this is the way that processor power management works in Windows. Oftentimes, client workloads are very bursty. They're intermittent pieces of activity. And so we'll put the processor in a very high power mode to get that piece of activity done as quickly as possible, and then we'll go back to the low power mode for as long as possible afterwards. And timer coalescing, which we'll explain today, is a good example of this concept. We want to expire a set of timers altogether and then have the system be idle for as long as possible. So I promise the rest of the deck is all about optimization techniques. So to get started, let's talk about processors. So again, the cost of the modern processor in terms of its maximum power consumption is absolutely going up. At the same time, performance and capability goes up. What's really interesting about processors, particularly those in mobile PCs today, is that they have a wide dynamic range of power consumption. They can be very, very, very low power when the system's idle, but they can consume lots and lots of power when they're being used at their maximum capacity. And that range of power consumption, frankly, is challenging both for the operating system and for applications to correctly manage and try to balance those out. So you can see here in the chart, right, that for idle for this processor, this is an example processor that we measured, very, very low power when the processor utilization is near zero. We're talking about hundreds of milliwatts. But as soon as you get to 10%, just a 10% CPU load, we're talking about a whole watt, so about a 10x increase. At 20 and 30%, they increment more. But look what happened when we got to 40%. Processors have these performance states where they can enter, and it's called speed step for Intel processors for mobile, but they can change their voltage and frequencies to deliver more performance on demand. And you see that as they deliver more performance, they consume much more power. So being really careful about CPU utilization is the first thing that we want to do when we optimize our application. Using less CPU is always a good thing. And we want to focus on when the application and when the system is idle. Now, going back to the second slide there with data, when we work with partners about optimizing pre-install images, we work with them to target less than 2% of CPU activity when the system is idle. A lot of people have asked me, where'd you get the 2% number? Well, we started by looking at the Vista SP1 installation. Vista SP1 consumes about 0.7% of CPU utilization when the system's idle and on AC power. And we think that 2% is plenty of extra room for value add and for OEM software on the system. And if we stick at 2%, you can see from the chart on the right that it's just minimal power increase. But if we get to 10 or 20 or 30%, we're talking about a much bigger impact on battery life and power consumption. So focus on idle. If your application is running and simply open, it should have very, very little CPU impact, unless it's doing something at that point in time that is important for the user scenario. But a lot of times we see background applications, services that are unnecessarily using CPU resource and don't need it to deliver their primary scenario. Now, after we've optimized idle, we want to focus on what it is our application does. If we're a notepad, we want to be the leanest and meanest notepad we can be and deliver as little CPU utilization with the most functionality as possible. And we want to do that for any application. We're going to talk about using the tools to evaluate how much CPU you use and how much CPU activity during a given scenario. And that can help you optimize optimize that utilization. As for specific tips, try really, really hard not to pull for state on the system. A common thing we see both inside Windows and working with application developers is pulling for state on the system. I want to know about a registry key, or I want to know about something on the disk, or my favorite is, I want to know if the system's on battery or not so I can do an optimization. Well, if the system's on, you're pulling for system battery state, that's not helping necessarily for battery power. We have, in Vista and later operating systems, we have a rich notification architecture for understanding if the system's on AC power or DC power, or if the user's chosen a high performance or a power saving plan. And we can use that notification architecture to be notified when those states change, as opposed to having to pull for them at 1 second or 5 seconds or some other interval. Now, I am a realist, and I realize that there are going to be times where you have to pull. There either isn't an event or notification infrastructure interface, or there's something that you just have to make work. Well, my request would be try to pull as least often as possible. Try to, at a minimum, please don't pull more than once a second. Once a second, more than that, starts having big impact on processor power consumption and even chipset and memory power consumption, depending on what that application's doing. If you do have to pull, we have a new timer coalescing API that we're going to talk about on the next slide, and that's about helping us extend those idle periods. So one of the big things we found when working through Windows 7 is that there's a lot of activity in the Windows system that, frankly, does have to be periodic. In many cases, we move people to events and notifications, but there's some basic things in the system that have to be pulled, that have to be iteratively looked at to have their functionality. A good example here is the kernel changing processor frequencies. We only know to change processor frequency by looking at past activity. And to look at past activity, we have to periodically pull to see how much busyness there was on processors. The thing is, though, that every time we do some intermittent piece of work, it kicks us out of a low power idle state. These processors, they have unbelievably low power when they're not doing anything. And the key is to get them to be as idle as possible and for as long as possible. They have it's pretty interesting. When you want to put a processor in a low power mode, it actually costs some energy to get the processor from the operational mode into the low power mode. And it costs some more energy to get it from the low power mode into the operational mode again. And that energy cost can be more expensive than being in the idle mode for a short amount of time. So in order to get low power idle states to work correctly, you have to be there for long enough for it to have a value. And if you're not there for long enough, then you probably shouldn't have gone there in the first place, because you're going to burn more power than you would have otherwise. So timer coalescing is a way of us squeezing together our intermittent activity, squeezing together timers on the system in periodic activity to get them executed all at once, and then to get the system to be idle for longer. So what we've got here on the slide, we've got an example. This is not real data, but an example of the intermittent activity. Now, Windows is driven by a periodic timer. So the 15.6 millisecond timer by default is an interrupt that happens to the processor all the time. And that's what we've got here with the blue arrow. Now, the green events, those are periodic timer events. And you can see they're relatively randomly scattered through the time here. What we want to do, gotta watch the slides. What we want to do is try to get those green events to be as close to the timer ticks and get them over with as possible. So you can see with timer coalescing, what it does is it allows the kernel to expire those events very close to each other and then re-enter that low power idle state for the processor. And that extends our average idle time and helps us avoid that transition where we spent more energy getting in and out of the idle state than we consumed while we were there. So the way that timer coalescing works from an API perspective is that it's just like set waitable timer. You tell us how often do you want to be notified that something has happened. But you now get to specify a tolerable delay. And that tolerable delay, you can say, I want it to be 45 milliseconds or 50 or 100 or whatever it is. A pretty good rule of thumb is that you absolutely want to specify a tolerable delay at least 33 milliseconds. At least give us 2 clock intervals to adjust the periodic work. But what's interesting is that many of the periodic activities we see in the system, they can have a large tolerance delay. So we're talking about things where we're maybe checking the disk for its size every hour. That can have a huge tolerable delay. It doesn't have to be every hour on the hour exactly to 0 milliseconds. It could be every hour on the hour plus or minus a couple seconds. So keep this in mind, that try to extend your tolerance if you use this API as much as possible. It enables us to schedule that timer expiration along with other things in the system. Now, the note about this, and we've got both the C interface here, and I've gone ahead and p-invoke the new interface for C#, and you can copy and paste this into your application if you'd like. The note here is that the period in this timer scheme is no longer guaranteed. So if you use a normal timer and you don't specify the tolerable delay, what happens is that Windows predetermines when your timer is going to expire. You might have asked for 50 milliseconds, but if we're using 15.6 millisecond intervals, you're going to expire in 44 or in 60. And what's going to happen is that as soon as you request that timer, we're going to set it up for the first time. But with timer coalescing, we may drift the expiration of your timer to line it up with other work. So that the period is no longer fixed, but the period is guaranteed to be within whatever you specified plus or minus the tolerance from the last expiration. This works really great for simple things where you're maybe polling in the system, where you've got to check on some piece of state that there's not a event or notification architecture for. Can be very flexible in terms of the tolerable delay. After optimizing CPU activity, probably the next most common thing we see with applications is inadvertent increases in the system platform timer resolution. Now, Windows is driven by the scheduler is driven by a platform timer that by default has a period of 15.6 milliseconds. This is an interrupt that happens to the processor. It causes the kernel to go off and schedule new work to check to see how busy things were. And what's interesting is that for some limited scenarios, that granularity of time may not be sufficient. So if you're doing some kinds of timing analysis, some kinds of animations, you may want, and even some kinds of multimedia, you may want something more granular than 15.6 millisecond timer expiration. And in fact, we've provided an API in the platform for a very, very long time that allows an application to do that. You can say, I need 1 millisecond granularity on my timers, and you call time begin period 1 in the multimedia DLL, and it just happens. The kernel scheduler gets invoked more often, and we go off and have fine-grained timer behavior. The problem is that 1 millisecond timer, it's another processor interrupt. It's another platform interrupt that now happens 15 times more often than it did in the normal case. And so we increase processor power and we increase system power accordingly. It's no different. It's just like the timer coalescing slide, right? It's a new event that happens on the system, and it happens more often, and it prevents us from being idle on the processor for long amounts of time. Now, a lot of times people say, how big of a deal is this? It's just a timer resolution. I need my 1 millisecond timer. It's pretty big impact. We're talking about taking a relatively idle processor, if we do nothing else on the system, from being hundreds of milliwatts to at least a watt. And that timer resolution, because it's a platform interrupt, it's not just the processor. It also impacts this chipset and the memory power as well. And you can see in this example system that we've taken this system from about 10.5 watts to over 12 rather, simply by increasing the timer resolution and doing nothing else. So the important part in our applications is to validate, to make sure if we need a timer resolution increase, we do it judiciously. We only increase it when we absolutely need it. Now, the next most common question is, well, how do I know? How do I know I did this? I might be using some library, I might be using some dependency, some application, software, or interface, and they increased the timer resolution. I had no idea that my application was doing that. Well, we've built into Windows 7 a diagnostic tool that we'll demo at the end of the presentation today to help you identify when an application has done this. And we now report what the current timer resolution is on the system and which application has made the request and what value they requested. Again, if you have to, my favorite request would be please don't do this. Please don't increase the time resolution. But if you have to, for an animation or a multimedia scenario or high precision analysis, do it only when you need to do it. Only do it on demand while you're doing that scenario, and then turn it back to the default when you're done. And even look to see if you really need 1 millisecond. Do you really need that fine of resolution? Because chances are you probably don't. you probably can get by with 5 or 10 milliseconds. And in fact, an interesting thing is DVD playback in Windows. One of the big things we did in Windows 7 to improve DVD playback battery life is to make this change ourselves. So we were at 1 millisecond resolution for audio and DVD playback in Windows Vista, and now we're at 10 milliseconds. And that's contributed to some of the battery life gains that we've had for DVD playback. This is a big deal. This is sort of the second thing I would do after optimizing CPU utilization. And again, use our inbox diagnostics. It's super easy to see when you're running your application if this has happened to you or not. So after processor power comes the disk. We're all familiar with the disk. It can spin down after a period of inactivity to save power. You can see from the chart here what the average power cost is. I would look at active idle, which is the middle bar here, and compare that to spin down. And we're talking about 500, 600, 7 milliwatts, 700 milliwatts or so. 700 milliwatts is a big deal. It doesn't sound like much. 700 milliwatts doesn't sound like much at all. But if you talk about a machine that's 9 watts when idle, like this notebook, that's a big deal. We're talking about 8 or 9% of system power. The catch for us as application developers is to make sure that we're not writing to the disk unless we absolutely need to. Now, if we're a file download program or a compression utility, okay, clearly we're going to have to write to the disk, and there's not much we can do about that. But the real thing to watch for here is when we're background activity. If we're a service and we're updating an INF file, or we're storing some state on the disk, or even flushing our state to the registry activity turns into disk activity under the covers. So be careful with how you read and write from the registry. It has the same impact as disk activity. And you can use the performance tools, which we're going to demo here at the end of the talk, to analyze, to see when your process is writing to the disk. What files is it accessing? How often is it doing it? Animations are a challenge for power consumption. Not going to lie about that. The reality is it's like everything else. You're doing more work on the system to deliver a better user experience. And that work, it costs power. There's not so much a way to get around that. Now, we try to optimize it as much as we can to have it use as little CPU and GPU as possible and as little memory as possible. But things like that have an increase in power consumption. And worse than, perhaps in addition to their power consumption and resource utilization, they also can prevent processor and GPU power-saving technologies. So GPUs have an interrupt. It's called the vertical blank interrupt. It happens at 60 hertz frequency. And if you're animating something on the system, we're turning that interrupt on to be notified at 60 hertz to know when to draw the next frame or when to render the next frame to the output device. But it's interesting. What we found is that a lot of times when we're idle and we're not rendering animations, we can turn that interrupt off. And it has impact on processor and system power consumption, about 1% or 2% for the average system. And we can turn it off when there's no animations to render. So if you do anything and look at any scenario, look at when the system's idle and sitting at the desktop. A lot of times in task tray icons, we see animations that are spinning. In fact, think about the network icon from Windows 2000 and Windows XP. Remember how it was the 2 little computers and they flashed the screen to see when there was network activity? We turned that off in Vista specifically because of this. That animation had impact on battery life. In the steady state, or when the system's idle, be very, very careful about animations, because not only are you going to do a little bit of extra work to render that animation, but you're going to prevent some underlying hardware technologies and hardware power-saving technologies on the system. And again, if we can, use environment. Use battery power, use the user's profile choice, use their power saving versus balance versus high performance. We'll talk about that in a slide too. Use those inputs to decide when you do or don't want to animate something. All of our applications, regardless of what they do, whether they be interactive, whether they be DVD, whether they be productivity, we almost always have a great opportunity to adjust to what's going on in the power management environment. The oldest thing that we've seen is when I'm on battery, I do something different, or I do something less, or I reduce my activity, or I reduce my period, or whatever it's going to be. But we can also do other things, such as look at the user's profile choice. In Vista and later, we have these 3 power plans now. We have power saver, balanced, and high performance. And you can register as an application for a notification when the user has changed between those power plans. And you can take different action in your application. You can turn something off. You can turn something on. You can really change your behavior and invoke a set of optimizations or invoke a set of performance reduction based on those pieces of environment. Now, if you want to get very advanced and very extensive, our power setting and power policy infrastructure, it's extensible. You can add your own setting. You probably remember from Windows Vista a setting in the advanced settings called search and indexing, where you could configure how the indexer's power mode was. And we're seeing third parties, ATI PowerPlay has a setting that's in there for GPU devices. Applications can interact and extend that interface if they want to. You can add a new setting, configure your behavior. You can have very fine-grained things, very global things, whatever you want to do. So when we talk about the idle floor on the system and reducing idle power, background activity, background applications and services and tasks, they have that's one big place for them to have impact on idle power. Now, the good news is that Windows provides rich infrastructure, rich task scheduler infrastructure, rich service infrastructure to help us make it really easy to implement that background activity in an efficient manner. And in fact, we're really excited today, this afternoon, next door at 1:45, we have a talk that does a deep dive on these technologies and shows you how to optimize your background activity for power, or maybe for reliability or performance or security. We've got a new innovation here in the Service Control Manager called Trigger Start. And this is about starting services only when they're required on the system. Many of you might be familiar with the tablet input service in Vista. It runs all the time, regardless of whether or not you have a digitizer or a tablet PC. That is fixed by this infrastructure in Windows 7. It's trigger started, only when a digitizer is detected on the system. And Vikram on our team is going to do a deep dive today on how you can take your own services, your own tasks, and move them to that infrastructure. Again, next door, 1:45 this afternoon. Lots and lots of rich details. So sleep and resume. A couple years ago, when I did this talk at PDC, sleep and resume was a really big problem. We were seeing a lot of applications that were not doing a good job of handling sleep and resume transitions. The good news is that that's getting a lot better from my perspective. We're seeing sort of the rise in mobility and intermittent network connectivity drive really great application behaviors around sleep and resume. They're often the same scenario, right? You lose network connectivity when you sleep the machine and wake it up somewhere else. An important change, though, that we made in Vista over XP is that sleep transitions, they can no longer be stopped by an application. You used to be able to say in an application, I don't want the machine to go to sleep, a lot like you can for shutdown. And we found that users were closing the lid and putting their machine in a bag, and they had no idea that it was still running. They'd pull it open later, it'd be burning toasty, and lost a lot of battery power. So the good news is that we can no longer prevent those. But it means that we have to tolerate them. We have to do a good job of working our scenarios around them. And on the suspend path, you're going to get these are the unmanaged notifications. There are equivalents for managed code. You're going to get a power broadcast suspend message. And this is a message that says, hey, the machine's suspending right now. You have 2 seconds to do whatever you want to do before the machine goes to sleep. Now, the good news is that there should be nothing to do. Calculator doesn't have anything to do. Notepad doesn't have anything to do. And the list of applications and scenarios that have anything to do with sleep is pretty small. Maybe if you're doing something on the network, you're a instant messaging application, you may want to update some presence, something like that. But super small amounts of activity that you should do. If you're an application that talks to a hardware device, it'd be a good idea to tell your hardware device that the system's going to sleep, that kind of thing. But should be very, very minimal amounts of work to do. Resume, though, that's the fun one. That's where you want to see what's happening on the system and reconnect or restart your scenario as seamlessly as possible. If you had a file open, try to open it again. If you cached it, open the cache copy. Think about the ways Word does a fairly good job, Microsoft Word does a fairly good job of handling these transitions very well. Think about how you can bring that experience to your application. Anything that you do here, try to get it back to the user as automatically and seamlessly as possible. Now, the other thing to be conscious of is that resources on the system, they may have changed while the machine was asleep. So not only may networks change, You may be different connectivity. A server that you were talking to may no longer be available. But all applications are using the system at the same time. We just woke up, and it may have been a long amount of time since we were running again. And a lot of applications are going to be trying to do the same thing you are and reconnecting to the network, trying to access the file from the disk. Just be conscious that the things you want to do here, optimize them as much as possible. They want to be very, very, very lightweight operations if you can. So I said that applications cannot prevent the system from sleeping. And that's partially true. They can only prevent the system from idling to sleep. So think about media center scenarios where we're recording TV. You may not be interacting with that system for hours on end, yet it never goes to sleep automatically. That's because the media center recorder is doing a good job of telling the power manager that, hey, I need the machine to stay awake. I'm busy recording your TV show, or I'm busy burning a CD right now, or I'm busy doing some work. And we have interfaces that have been around for a very, very long time that show you exactly how to do that. Many of you are probably familiar with set thread execution state, an API that allows you to say, keep the display on or keep the system awake. A problem we have with this is that any application can make that request. And end users, they expect the machine to go to sleep in the way that they configured it, particularly in the enterprise IT scenario. We're seeing lots and lots of enterprises that they want their machine to go to sleep after 30 minutes because they want that power saving. But it's hard for them to figure out which applications, which software, which drivers might be preventing that machine from idling to sleep automatically. So one of the cool things we've done in Windows 7 is that we've provided new inbox diagnostics, which I'm not going to demo, but you can try in the M3 build, that enumerate these outstanding requests. You can say power config exe and type requests on the system, and you'll be able to see outstanding application requests. And in fact, we built a new API here that allows applications and system components to tell the user why they wanted the machine to stay awake. So it's pretty good. It's pretty good to know which application did it, which service, which process. But you really want to know is why. What was going on? What is it about their configuration? What is it about their task? What thing are they recording? What thing are they burning? What's going on? And so we built new APIs called Power Create Request and two siblings that allow application callers to pass a localized string reason for why they want the machine to go to sleep. It's also way, way, way better than set thread execution state. So many of you may be familiar that set thread execution state is a per thread reference. We've built now, these are handle-based APIs. They work across threads in a process. The set thread execution state also had this flag called ES continuous. And depending on when you set it, it either meant reset the idle timer. So if it was 10 minutes, now I want it to be 0. Or it meant don't prevent the machine from going to sleep until I call you back again. That difference is pretty dramatic and very, very hard to get correct. And these new APIs, they no longer have that duality of use. And then the diagnostic information that we can provide in these APIs is very, very rich. In fact, you can experiment if you want with Windows Explorer. Copy a big file in Windows Explorer on the pre-beta build that you got today, and then drop to a command line while it's copying and type PowerCFG requests /verbose. And you'll see a text reason from Explorer saying Windows Explorer is copying files. We've implemented that in some system services, and we're starting to work with partners and application developers to implement the reason codes as well in applications. So I wanted to, PDC, should show some code. Wanted to show you how to make this work. Very, very, very easy. Relative to set thread execution state, I think much, much easier to understand, even though it can be a couple more lines of code. So when you want to make this thing work, what you do is you create an object or a structure called a power request context. And this is the thing that stores that string, stores that context that you want to have. And in this example here, I'm setting up a very, very simple diagnostic string for an example application that might be downloading files. You can imagine maybe this is a web browser or something that's downloading files, or whatever or an FTP client, or whatever you want it to be. And so you say the version is, this is a version structure. You set the default version. And then you say, what kind of context is it? Well, this is a simple reason context, just a literal string that I'm providing. We do support substitution, so you can say, I'm recording TV on channel 35. It's an option. And there's a different flag for that. And then you provide the reason string that you want. After you set up that structure, you create a request, and this gives you the handle to the request object. You pass in that context structure, and you get a handle back. And then after that, that's where you get to say, what kind of request is this? We support keeping the display on, or a display required request. We support keeping the machine from idling to sleep, and that's called a system required request. And that's the version we're using here in power set request. And then we also support away mode required request, which is enabling a pseudo off state we call away mode. This example uses the set request API. You pass in the handle to the power request, and you pass in what kind of request do you want. In this case, we want a system required request because we're downloading files. It's OK if the display goes off. We're just downloading files. But what we want to prevent is the machine from going to sleep. Make the request, wait till your activity is complete, and then you clear the request. Pass back in that handle again, and the request goes away. Now, you can use the object again if you want. Let's say you're downloading multiple files. You might want to increment and decrement using the set and clear APIs. That's an implementation option as well. The managed p-invoke code and this exact sample is in the back of this deck. So if you go online and download the deck, you'll see exactly how to make this work in C#. This is one of those slides that, in the slide review, definitely caught people's attention in the back of the room. It's pretty funny in some slide reviews. You get a wide audience, and then a few of them started perking up about this slide. We need to be very, very careful when we're building applications to understand the power impact of the dependencies that we have. Now, my advice is Microsoft provides a wide basket of technologies to deliver it and develop applications in. Wide basket, and they're all great. And they're all good for a variety of scenarios. The thing that I would ask you to do is to consider all of your goals for application development. Consider presentation. Consider performance. Consider energy efficiency. Consider power consumption. And then choose the right scenario and the right tool set to build that application. The one specific piece of advice that I will give you is be really, really conscious of activity and resource utilization on things that are long running on the system. If you're developing a service, an NT service that's going to be on the system, or an application that's going to run for the entire boot duration, build that thing to be as lightweight as possible. That's only good for power. It's only good for performance. It's only good for memory footprint and disk footprint. And then, of course, whatever you build, regardless of what you build it in, measure and validate. Use the tools. We're going to demo them. Look at perf counters. Look at the managed performance tools. Look at all of the different tools to validate the impact that that application is having on the system. OK, demo time. Very, very, very excited about the demo. So one of the things that happens a lot at Microsoft is we'll be working on a new version of Windows. And so, of course, everybody wants to try it out. You want to grab that new version of Windows and put it on your system and play with it. And mobile PCs are super, super popular. Almost everybody at Microsoft has a laptop these days. And so they'll install the latest version, and they'll go, huh, my battery life, not as great as the last version. So they'll say, I installed Windows 7, my battery life, much worse than Vista, or a little bit better, or a little bit worse. And often what happens is that this request comes from an executive. They'll say, I installed on my laptop, and now the battery life's awful. Fix it. Figure out what's wrong. So we'll grab their laptop, grab a kernel debugger, a couple guys, 3, 4, 5 hours later, we'll come back with a list of here were all the things that contributed to your bad battery life. It might be a bug that's known in a problem, in a service or an application. It might be you're missing a driver. It might be you needed a firmware update. You need what have you. What the power efficiency diagnostics do for Windows 7 is they do that task in 60 seconds. They identify the top 8 or 10 things that are really, really bad for battery life, that are really, really bad for power management, and they show you on the system what the root causes of those things are, what the problems were. It's a wide variety of diagnostics. It does things with hardware, with firmware, but it also looks at applications. So the timer requests that we talked about earlier in the slides are available here, as are processor utilization and policy settings. We wanted to take a very holistic view at what is it that's causing problems on the system. It may be specific to device, or it may just be that the policy settings you chose, they weren't ideal for battery life or energy efficiency. Now, this utility is baked into Windows 7, and it's available in the pre-beta build that you have here at PDC. and you can run at the command line, and I'm going to show it to you. You can run this tool, and you can generate an HTML report. OK, just give me 1 second. So what I've got here is the pre-beta build. It's a fairly small laptop, big battery. This battery is 74 watt hours, and the machine, when I'm using it, is anywhere between 10 and 12 watts. So we're talking about a 6 or 7 hour machine, typically on battery. Now, I've simulated a set of problems on this system to do the demo today. And what you can see is that, well, it's taking a second. I just unplugged it. We're going to see how much battery life this machine has. And we're going to see that it has a surprisingly short amount of battery life, given how much charge we have. So we've got 98% charge remaining on the system. So it's almost completely charged. But it's saying only 2 hours and 43 minutes in the battery meter. And I would have expected at least 5, maybe 4.5 at worst case. So I'm going to use the power efficiency diagnostics to figure out what's going on. So I can create a new elevated command prompt. So CMD, and then right-click administrator. And then Power CFG is available in the box. You can run it from any directory you want. So you run Power CFG and then type energy and watch. What we've done is we've added a lot of ETW tracing and a lot of event tracing to the Windows kernel and related services on the system. So all of those things that we want to diagnose, whether they be how USB devices are working, how processor utilization is going, firmware support, policy, we've instrumented all of that. And then we're turning that tracing on and watching it on the system for the next minute. And we get a bunch of initial data about configuration and policy choices, and then we watch intermittent activity. So we're looking at what's on the CPU and how much CPU time is it consuming. What's the timer resolution? And our applications dynamically changing it. For USB and for our OEM partners, we look very closely at USB devices and their suspend support. USB has a big impact on processor power consumption because USB devices result in high-frequency DMA transactions that prevent low-power processor modes. So 60 seconds, you can change the duration if you want. The result here is going to be an analysis and a set of errors. In this case, the system's found 3 errors and 4 warnings and 13 pieces of informational data. Now, the result is an energy report. It's called energyreport.html, and it opens in IE very, very easily. No extra parsing software required. And so what you can see here is we've got an example system. It tells you some information about the system's capabilities and number of threads and processes. And then we start listing errors. So the errors that are in red here, these are big problems for battery life. These are things that we know are energy efficiency. We know that these things are big impact. We know that they're anywhere between 5 and 10% at least of battery life impact. So the first one is that somebody changed my power policy to maximum performance, and I'm running on battery. Now, for the wireless adapter, this policy change is about 800 milliwatts to a watt, or maybe 8 or 10% of the system's power budget. So that's definitely a big deal that I'm going to want to fix on the system. And then I've also got high processor utilization. I was idle. I wasn't doing anything on the system other than running that diagnostic utility. Yet my processor utilization is at 51%. Definitely a problem for battery life and energy efficiency. We're talking about lowering the idle power of the system. And this diagnostic utility is all about how to identify what's preventing that. This system also has a PCI Express capability disabled in the firmware. So now for warnings, these are other problems on the system that may have less than 5 or 10% impact, and maybe by design or maybe not. So it's important to look at the information to see what's going on the system. So here we were talking about the timer resolution. You can see the maximum or the default on this system, stress again, is, that's not working very well, I apologize, is 15.6 milliseconds. The units here are 100 nanosecond units. And the current timer resolution is 10,000 100 nanosecond units, or 1 millisecond. So this is that 1 millisecond problem that we were talking about at the beginning of the slide deck. So here you can see, I wonder who did it. I wonder which application caused the problem. And in fact, it's this application here called CPU consume, which is a test application we built to consume processor resource needlessly. It also increases the timer resolution. And you can see exactly what timer resolution it requested and what the process ID for this process was. Now we've got some other warnings here about the 802.11 policy is set to maximum performance when I'm plugged in. If I wanted to optimize my energy efficiency on a desktop, I might change this policy. And then you can see which process is it that had significant processor utilization. And during this trace, it was CPU consumed, this test application. And you can see its average processor utilization, and within it, which modules in that process are consuming the large amounts of CPU. Then we've got a set of informational data about the system, what the current power plan was, what the personality of that plan was. I'm running on balanced. Some key settings that we talk about for idle or DVD playback. Successful analyses for system availability requests in USB. Nobody was keeping the machine awake. USB suspend was working properly. And then a very interesting one here at the end about battery information. So a common scenario we have is that somebody will install the latest version on their system, and it'll get 20 minutes of battery life or 30 minutes of battery life. And they'll sometimes say, oh, it was going great. It was going 40 minutes, 30 minutes, 20 minutes, and then it fell off at the end, and it drained immediately. Oftentimes, that's due to a battery that needs to be replaced, or a battery that's beyond its normal lifespan. And so what we're showing here in the battery information is the design capacity of the battery compared to its last full charge capacity. And the design capacity is in, this example is in milliwatt hours, but it's how much was the battery built to hold. And then the last full charge is the last time I charged the battery, how much did it hold? And the ratio of those two together can be very useful in determining, frankly, how old that battery is and what stage does it need to be replaced in. In this case, it's in great health. It's maybe down 2 or 3%. I've had this battery for a couple months. And in fact, when I first purchased the battery, last full charge was greater than the design capacity. I had a couple extra percent in the system. So again, my battery life was 2 hours and 35 minutes. I'm going to go into Task Manager and take care of this CPU consume application. So I'll take care of that. I'm going to go in and take care of the power policy issue that we identified. So click in here. I'll set this guy to medium power savings. And I'll start looking at the battery meter to see how much time I got back. So I'm already at 3 hours and 17 minutes. The battery meter averages slowly over time, 4 hours and 15 minutes. So this can be a good way, let me put this up so it's, this utility in box can be a really good way to see what is it on the system that's impacting battery life. And some of those scenarios apply very, very well for applications and for application developers, particularly around CPU utilization and those timer resolution requests. Again, you can try this out. I'm going to be in the lounge this afternoon if anybody wants to go over it in more detail. So the last diagnostic tool I want to talk with you about, and I apologize, we're going to run just a few minutes over, but I think it's really, really important to go through this, is what we call the Windows Performance Tools Kit. Many of you probably saw there was a video session for this, and there's also a hands-on lab. I saw several folks working through it yesterday. If you think of Power CFG and the energy tool, sort of the high-level, tell me what's going on my system, broad scope tool, XPerf and the Perf Tools Kit is the deep dive analysis tool. This is the tool you use when you want to know what function in my application is causing the excessive CPU activity. What thread is having a problem? What files am I writing to? What disk activity is happening? You need to use probably both utilities to see what's going on in the system. Now, XPerf, the good news is not limited to Windows 7. You can go get this today on the web. This link translates into downloading it. It works great for Windows Vista. You can start analyzing things today. And what I'm going to do is I'm going to show you very briefly the first hands-on lab. So we have a hands-on labs for this. I'm going to show you very quickly the first exercise in the hands-on lab. Now, after you install, I apologize a little bit for the screen readability here. When you first install the Performance Tools Kit, you'll get a Start Menu option. You'll get a Program option. I've installed very quickly. And so the utility that you use is called XPerf View. And it's a viewing utility that lets you see what's going on the system graphically. And as you work through the exercises in the hands-on lab, it teaches you how to create trace files. And those trace files, they're the same trace files that back the energy tool. You've enabled tracing, you've watched it for some amount of time, and then you've recorded that trace file, and you're going to analyze it post-recording. And so I'm going to open one that I've already have saved on the disk. So a couple things come up here immediately. The organizer is viewed into panes, and you can turn You can see over on the frames here, you can turn things on and off. You can turn CPU time on and off, disk on and off, DPCs, what have you. But if you look at just this basic first frame, it's about CPU activity on the CPU and percentage of utilization. And you can see this very, very interesting pattern of bursts of activity roughly every 10 seconds, pretty much. And they consume 100% of the CPU every 10 seconds for just a little bit amount of time. And what you can do with the, and take a look at the bottom one here. You can see we talked about processor frequency changes. You can see that those bursts of activity, they caused us to take the processor from a low power mode to a very, very high power mode to finish that work. And you can see if you look at the idle time in the middle of these bursts of activity, we can analyze it to see how idle the system is. So I've selected an area, and I'm choosing summary table. And you can see here, again, the screen readability is... So the screen readability here, you can see that idle. So idle process is how much idle time do we have on the system. And you can see that we were 99.42% idle. That means every other piece of CPU utilization was about 0.5% of CPU activity. So it lines up with that 0.7 that we were talking about for Vista SP1. Now we might want to know what's causing these little bursts of activity, which application, which process, which thread. And so we can highlight these areas as well. So I'm going to highlight one here and right-click and choose Summary Table. And we'll see more details about that activity. And you can see here, let me zoom in again. So you can see here's the percent weight. This column is the total amount of CPU time relative to the trace, or the amount that we selected. And you can see that one of these is 57.47, the other one's 41.38. If we scroll over here to the left, we'll see that the PDC hands-on lab application, process ID 1948, is responsible for 41% of the CPU time during that piece of the trace. So this application is the one that's causing the problem. And this is really, really rich for developers. You can zoom in on which functions, which modules. You can, if you have symbols for your application, you can load symbols, and you can see which functions are being called at what frequency. And definitely encourage you to take advantage of the Performance Tools Kit. Download those for Windows Vista today, and take advantage of the hands-on lab if you get a chance here. So very briefly at the end, if I asked you to do nothing today, I would ask you to understand that application software and software in general, it has just as much impact on power consumption and battery life as does the hardware and the OS internals. And it's important that we optimize that application software for energy efficiency, for battery life, for power consumption. And the way we do that is we focus on resource utilization. We focus on the amount of CPU, the disk, the timer resolution that we have. And we take a really, really close look at idle, because we want to lower that floor for idle power consumption. We want to reduce the amount of idle power, because that's going to translate across all the scenarios that the system is used in. We've got great infrastructure to help you out, particularly if you're going to do background activity. Lots of new infrastructure in Windows 7, a robust task scheduler, a service control manager, to help you schedule those pieces of background activity intelligently, based on AC power, based on DC power, based on when the system's idle. And then finally, use the tools. Use the power efficiency diagnostics in Windows 7. Use the performance tools kit to analyze in rich detail, and use those tools to look into your application. Look in to see how much CPU, how much disk, where can you optimize, what performance optimizations are available. And then the last one here is take advantage of a bunch of great resources that we've had online. We've got a paper that's out for Windows Vista and applies equally to Windows 7 about how to optimize applications for power, how to handle sleep and resume transitions. And a really cool thing is we've got a sample Visual Studio project that we put up 2 years ago about how to receive those notifications, how to look and see when the system's on AC power versus battery versus power policy changes. There's a good article on MSDN about power-aware WPF apps, how you can interact with animations and storyboards based on those power notifications, and then a variety of other resources here around managed code interop for these APIs and using the performance tools in a power test utility. These are the backup slides. And of course, I would very, very much appreciate you filling out your evaluation form. And we'll take questions here for probably about 2 or 3 minutes, and then I'm going to go outside and then go to the lounge, and I'll answer everybody's question.
So thanks for all these new tools. I'm really excited to take a look at them, both as a user, see what people are doing on my system, and our app can take advantage of them too. I wanted to mention one other thing about platform timers outside of power savings is if you crank down the interval on the platform timer, that really affects virtualized environments as well. I know in particular VMware, for example, on OS X, which some people may use, if you crank down the platform timer, they have a hard time virtualizing that, and it really spins up your host processor. So you got to be aware that even though your system, there might not be anything else going on your system, in this case the guest, but you're taking away resources from the host side as well when you do that. So
yeah, I think that's a great point. That's a great point.
Okay, my question is, what is the power impact from the Windows Arrow for Vista in Windows 7? Or is it behaving differently when the system is running on AC and DC?
Yeah, so the question is about the impact of Windows Arrow and the new graphics engine and what have you on Vista versus Windows 7. So even on Vista, so if we've looked at Vista SP1, in fact, we've had OEM partners that have brought us instrumented data from Vista SP1 with Arrow enabled and with classic mode. And they see almost no difference. We're talking about way, way less than 0.1% difference. And in some cases, it's in the margin of error because sometimes they do the run, Arrow is better. Sometimes they do the run, classic is better. So the impact is basically nil, basically zero.
That's good. Thank you.
Yep.
So there was a lot of great ideas you showed us here. But when I see my design team, my development team, I think the most people, they're so stressed out with implementing features, they had definitely not the time to care about that. On the other side, you have the consumer. When the consumer have a laptop and he said, oh, on my laptop I want a news ticker running or what else, small application, possibly needs 50% of the background power. You don't know. So what I would really like on both sides, when Microsoft would start a logo program, would say maybe green Windows, green Windows hardware, green Windows memory sticks, for example, is also a big issue. Some very low, some very high. Who knows? And with all your tools, green application. And then people say, oh, I want to optimize my battery life, and I look for such products.
Yeah, so the question's about what can we do in terms of a logo requirement, or even I'd extend your question around diagnostic tools for the end user. So we demoed things today that are good for developers and good for OEMs and good for folks that know their way around the system, but certainly not set up for end users. And the way I'd answer your question is that it's hard. So I would love to do those kinds of things. The thing I want to do first is figure out how do I take those diagnostics that I showed you guys, how do I make them available to the end user, improve their accuracy as much as possible, and message them in a way that works for the ecosystem. If that were some third-party application that one of us in the room had built and sold that was having that was flagged in those diagnostics, I think it's very hard and very risky the way that we present that to the end user. And so we need to be very, very careful about how we do that. I agree that we want to head down those directions, though, in the future. No disagreement. Let me take a question up here first.
Do you have any tools that would help me measure the impact on battery when if my application starts at Windows boot up or comes up? How do I automate that and find out my impact on battery?
Yeah, so the advice I would give you today is to do a before and after test with your application installed or started or not at boot. And I wouldn't look at battery life. It's very, very hard, even for us at Microsoft, to automate the battery life rundown, to automate a time, or to automate power consumption. We are in the process of trying to do a better job of that. Instead, what I would encourage you to do is look at your service or your background activity and look at the resource utilization for it. Look at how much CPU time it takes when the system's idle or during boot. Look at disk footprint, and look at, particularly if you go to the talk this afternoon, we'll talk about boot up time and shutdown time. It's frankly very challenging. And I would tell you to look at CPU time and then maybe do a before and after.
And it all has to be manual? There's nothing that we can...
There's nothing great for automating that today. Okay. I want to get there. I want to get to the point where I can measure... the system can tell me how much power it's consuming and have that be accurate. And then you could automate on that. But we're not there yet.
Good presentation, Pat.
Thank you.
Just a quick, I've got a couple of questions, but I'm just going to ask something relevant to your presentation.
Okay.
You got the thread execution state, and you got the power set config, set request, and you got the set available timer and set available timer X, right? Does the power config tool work with the older calls?
Yes, that's a great question. So we actually do instrument the older set thread calls.
Yeah.
We will show the process or the service that set thread call is attributed to. We won't show the diagnostic string. You can't provide, there's no way in the set thread API to present a reason or a text string, but we will identify which applications. In fact, you can demo yourself. Try PowerPoint and do full screen presentation, and then drop to power config and look at the request. You'll see that we annotate PowerPoint because he's correctly keeping the system awake and keeping the display on while you're doing a presentation.
Fantastic. And just related to that, power config, is any API exposed to me as an application developer to actually query those states?
That's a great question. We haven't decided yet.
Okay, cool.
Well,
it'd be cool.
We can talk offline.
All right, fantastic.
We can talk offline. That's a good question. Yep.
Is any work done in order to disable unused hardware on idle process? And for example, in your case, in your demo you provided, the network card wasn't being used. I mean, you was not connected to network. So I not really care about high-low power consumption of this device if operation system will just disable it when they not use it.
Yeah, that's a great question about disabling devices and power impact. So one of the things, an example of that is one of the things we're doing in Windows 7 is the networking team has gone off and built, they call it D3 on disconnect, but it's basically runtime idle power management for that device where you put that device in a low power mode when the cable's disconnected. All of us have laptops and we're almost never connected to hardwired Ethernet. And so that's an example of what they're doing. They're putting that device in a low power off mode automatically. And actually parts of the system already do that. The disk is a good example. Some set of audio codecs already have that functionality. One of the challenges we have, though, is that we don't want to simply disable them in the classical sense of device manager, because you don't want to disable them and then have the user want to insert a USB key or connect to a network and not be clear as to why that functionality is no longer available. So the technique that we're applying is, of those devices that support power management, implement it in such a way that it's automatic. It enters the low power mode automatically, and it exits the low power mode on demand automatically, so that we don't have the user experience pain of those things on and off. And the last thing that I would add to that is that simply disabling those in an application may or may not have a power win. Sometimes you'll disable a device in Device Manager, and the power consumption for that device will go up because that driver is no longer running on that device and no longer capable of putting it in the low power mode.
Yes, but actually, in some cases, you can detect whenever the device in use or not. For example, as me disabling Bluetooth device, and I always can detect whether the user want to connect it or no. I actually doing this right now in Vista Battery Saver.
Sure.
So you can detect in some cases.
Some cases. So the Bluetooth stack's a good example, right? They have a mode called sniff mode where they can be in almost off, really, really close to off, and they can wake up when they see new devices. It's not different than the way USB suspend works and what have you. But I think the thing that I would caution you against is being careful about low power modes that are automatic versus disabling that device in the classical sense. Those are different things.
Okay, thank you.
Yep.
So you had called out that the string that's displayed to an end user as to why they can't shut down was localized. Is it going to be supporting MUI so that multiple users that are logged in using different languages will get their own localized
Yeah, that's
version?
a great question. We're having a challenge with that right now, in fact.
Okay.
It does. So PowerConfig.exe, the command line tool, does. Because what it does is we store the resource and the ID, and then we go up and in the caller's context, in the caller's locale, go off and get that resource and the ID. So we put them back together using the right thing. There are some challenges in some other scenarios. If you want to talk offline, we can talk about that.
All right, thank you.
Yep. All right, if there are no more questions, I'm going to be outside or in the lounge. Thank you very much.